Electrolytic cell is a second kind of cell. It's different from electrochemical cell. In electrochemical cell, what happens is the chemical energy produced through that is produced through redox reaction is being converted to electrical energy. But what happens in electrolytic cell is the reverse of it. We'll pass electricity to a container containing electrodes in it, and will make the chemical reaction happen. So it's a reverse of electrochemical cell. In electrochemical cell, the redox reaction produces electricity, and here we will inject electricity, we'll pass electricity through the solution and make a chemical reaction happen. That is called electrolytic cell. There's one very important law that that describes the electrolysis, and it has been propounded by Michael Faraday. So it is called Faraday's law of electrolysis. Electrolysis. Electric current is used to do lysis, means it's like dividing, separating, or making chemical reaction happen. The first law states that the amount of chemical reaction happens. So see, electrolytic cells means a chemical reaction will happen. So how much chemical reaction will happen is proportional to the quantity of the electricity that is passed. It's quite obvious, I think, right? You don't need to remember it. The amount of electrolysis means electric energy will be passed through a solution, and a chemical reaction which is not happening on its own, which is not spontaneous, we will make it happen. So a non-spontaneous chemical reaction will be made spontaneous by passing electricity to it. And how much chemical reaction will happen by passing electricity, it depends on how much the quantity of electricity that you are passing through. And what is meant by the quantity of electricity? Electricity, it's actually, if you go through physics, is what is electric current is a rate at which the charges pass through, and that is called electricity. There's a relationship, like we write I equal to Q by T. Q represents the charge and T is the time. So how much at 1 second, how many charges are passing through a wire or a conductor is called the electricity. But what is the quantity of electricity? It will be Q, the charge pass, and it will be equal to the product of I, that is electric current, and the time. How much time you are passing? You are making electricity pass through it. That will be the charge. That will be the quantity of electricity. So how much chemical reaction is happening, or the quantity of chemical reaction that is happening through electrolysis in the electrolytic cell. Okay, electrolysis happens inside the electrolytic cell. It depends on the quantity of the electricity passed through it. So this is the first law. The second law states that the amount of substance liberated. So you are passing electricity, and there will be two electrodes, and two inert electrodes which will not react with electrolyte, maybe platinum or gold. So amount of substance that is liberated at the anode or in the cathode by passing electricity in the electrolysis that is happening inside electrolytic cell, the amount of substance liberated or quantity of the substance liberated, it's proportional to the chemical equivalent. It's proportional chemical equivalent of the substance. Suppose you are passing to same amount of electric current, but how much quantity of the substance will form? A metal, it may be silver, or suppose it may be silver, or it may be magnesium or aluminum. How much silver or how much magnesium or amount of aluminum is liberated at the electrode? It depends on when you're passing suppose same quantity of electricity, right? It's a solution of silver, it's a solution of magnesium, or in solution of aluminum. But what is the quantity of the silver form, or what is the quantity of the magnesium liberated, or what is the quantity of aluminum liberated? It depends on the chemical equivalent of the substance. The term chemical equivalent actually it's very much this particular term maybe you have learned in class 11, but the origin of this term is the electrolysis of is the Faraday's laws of electrolysis. This particular law, it defines what is chemical equivalent. Chemical equivalent, how it is defined? It is defined as you divide the atomic mass of the metal. You know the atomic mass. Suppose the atomic mass of silver is 108 U. divided by number of electrons that is required to reduce the cation. So these are cations. How many electrons are required? It's for silver only 1 electron is required. For magnesium 2 electrons are required, and for aluminum 3 electrons are required. So whatever is the atomic mass of the metal, you divide it by number of electrons required. For example, for silver you will divide by 1. For magnesium you will divide by 2. For aluminum you will divide by 3. Fine. So what is the atomic mass of silver? 108 divided by 1, because it needs only 1 electron. What is the atomic mass of magnesium? Atomic mass of magnesium is 24 divided by number of electrons divided by 2 is 12. And for aluminum, the atomic mass is 27 divided by number of electrons is 3. 27 divided by 3. Whatever you're getting is what? It's called the chemical equivalent. Chemical equivalent of silver, the chemical equivalent of silver will be 108 divided by something, by 1. The chemical equivalent of magnesium will be 24 divided by 2. The chemical equivalent of the aluminum will be 27 divided by 3. Right? So these are the chemical equivalents of these metals. So the quantity of the amount of substance liberated at the anode or in the cathode, it depends on the chemical equivalent. It depends on the what kind of element it is, because chemical equivalent is what? It's a property of that metal of that substance, right? The chemical equivalent of silver will be 108. Magnesium will be 24 by 12 by 2, that means 12. Aluminum 27 divided by 3, that is 9. So it will be 8 gram of silver, so 108 gram of silver, or 12 gram of magnesium, or 9 gram of aluminum. So how much of the substance is formed, is liberated? It depends on what kind of metal it is, or what kind of substance it is, or what is the chemical equivalent of those substances. So quantity depends on the amount of substance liberated through electrolysis in the electrolytic cell depends on the chemical equivalent of the metal or of the substance. Fine. This is the Faraday's laws of electrolysis. If you understand this, then we'll move on to the next topic. So what are battery? Batteries are again electrochemicals, not electrolytic cells, electrochemical cells. It is divided. There are two kinds of batteries. One is known as primary battery, and another is known as secondary battery. Primary battery, for example, dry cell. We also call it Leclanche cell. Its potential EMF, electromotive force. The difference between the electrode potential of the two electrodes that we use is 1.5 volt that we usually use in our remote of the AC or clocks and all. Those are dry cells. There are two sizes, right? AAA and 2A. Those are dry cell, or we also call it Leclanche cell. And there's one more cell that we use in small devices, watches and all, that is called mercury. And its cell potential is 1.1 volt. It's a little lesser than the dry cell, but it's a very constant source. So we get a constant source of a DC, direct current, through these batteries. Here, what happens? What is batteries in electrochemical cell? Well, chemical reaction, the redox reaction, it gives rise to electricity through. But here, what's the difference between primary and secondary? In primary, that chemical reaction or that redox reaction, it happens only once. But in secondary cell, that redox reaction, after it's completed, after reacting, all the reactants become product. The product can again be reversed by passing electricity. It can again be the chemical reaction can again be reversed, so that the products are again formed from the reactants. So it can be the chemical reaction, the redox reaction, which give rise to electricity. It can be done again and again by passing electricity through it. In other words, it can be recharged. What is so those batteries which can be recharged are known as secondary battery. And these primary batteries, they cannot be recharged. Once redox reaction is over, it will stop producing electricity or electric current. But here, what can be done is that after all the reactants are converted to products, the electricity stops. What we can do is we can again pass electricity to it, and the products will become, the reaction will be reversed. The products will become reactants, so that it can start. It's recharged. The product becomes a reactant. It is recharged. After that, the chemical reaction will again start, and these are called secondary batteries. The most common example of secondary battery is a lead storage battery that we use in our cars or in bikes. Here the anode is lead, The cathode is lead dioxide, and the electrolyte, that is used sulfuric acid. It's contain 38% of sulfuric acid in water, distilled water we use. And then there's one more secondary batteries there. We call it rechargeable nickel cadmium cell that we use in the camera and all the DSLR cameras. There we use nickel cadmium cell, or in mobile phones also. Those are nickel cadmium cell. Those are also rechargeable. So whatever, all the rechargeable batteries that you see in small devices are either this one, or in the car, or in the car, or in the buses, or in yes, or in the bikes. Those are lead storage battery. This is one of the most common form of battery that we use. One more cell called fuel cell. What happens is we use the anodes, the fuels. That means the anode and cathode. They are supplied. They are supplied. The fuel they can be supplied continuously, so that electricity is generated continuously. For example, in fuel cell, its efficiency it's much more than the batteries, the primary or secondary batteries. The efficiency is around 70%. So whatever fuels that the fuels that are using gives high amount of energy. So it's much better than the thermal plants from where we are using this electricity, whose efficiency is only 40%. So fuel cells are better. And fuel cells, what happens? The most common example of fuel cell is where oxygen and hydrogen are fed continuously, and it produces electricity. Fuel cell is a cell which produces electricity. The only difference is the chemical reaction happens. Whatever the chemical reaction happens, the redox reaction happens. The anode cathode, whatever it is, it's fed. It's continuously fed. So electricity is continuously generated. Here, what happens in cathode? Cathode means where reduction takes place. So consuming well, something is reduced. For example, here oxygen gets reduced to form hydroxide ion. Here, what happens in fuel cell is oxygen reacts with water with using 4 electrons. Oxygen and it is reduced to hydroxide ions. It's aqueous form. In anode, oxidation takes place. The hydrogen is oxidized. Whatever hydrogen you're feeding is oxidized to this hydroxide ion and becomes water. So the end product is what? The end product is water. See, this is the whole reaction. Hydrogen and oxygen reacts from water. See, so fuel cell is like environment friendly. There's nothing. The end product is not poisonous or it's not harmful to the environment. So it's environment friendly. Hydrogen and oxygen reacting and forming water. And what's the chemical? This is the overall chemical reaction. What happens in the cathode combined plus what happens in the anode. And this is the reactions that happens inside the fuel cell, right? Oxygen is being reduced to hydroxide ion, and hydrogen is oxidized to form water. So oxidation means is consuming oxygen. Consuming electrons, and in oxidation, electrons are produced.